Hello, are you there? Okay. Can you hear me recently? Hello? Okay, it seems that you I haven't shared the slide with you, right? And by the way, do you hear my voice recently?
Yes, teacher.
Yes. So
Yes.
Oh, just now.
Just now.
Oh, just now. Okay. Okay. Perhaps I forgot to turn it on. So perhaps let me go over this slide a little bit. Um, now I want to talk about the approximation, the property. We have three distributions here, right? The three distributions have the same mean values, right? The second distribution is a Poisson distribution with the parameter lambda. So the mean is lambda, which is 4. The first distribution is a binomial distribution with n 16 and p 25%. Okay. And then the mean value is n times p, which is 4. For the large distribution, you get 100 times 4%, which is also 4. You see that the three distributions have the same mean values. However, the first and the second distribution are different, right? But it is normal to see that they are different because the first one is a binomial distribution and the second one is a Poisson distribution. But when you have a look at the last two distributions, then you can get a surprise because they look very similar to each other, right? Even though they are two different distributions, right? The first one is a Poisson distribution. The second one is a binomial distribution. But when you have a look at the graphs, you see that they are about the same, very similar to each other, right? If you can have a look at the first column, the second, the third, the fourth, the fifth. You can compare all these columns and you see that they are very similar to each other, right? It's really hard to recognize the difference between them. What happened in this case? Well, in fact, in the last case, in the last distribution, n is 100, which is really big. No, I'm not saying that it's not really big. It's just quite big, right? Big enough, 100. In the first one, in the first case, you have 16, which is not big already, obviously. So we can think that if n is big enough, a binomial distribution will be very close to a Poisson distribution. Is that true? Is that always true, or this is just coincidence? Well, in fact, it is always true. When n goes to, we can prove that if y is a Poisson random variable and xn is a binomial random variable with the two parameters n and pn, where pn is lambda over n. So you can see that n is bigger and bigger and pn is smaller and smaller. Lambda is a fixed value, it's the constant. Then when you compare the limit n goes to infinity, the probability of y equals k over the probability of xn equals k, that limit is 1. It means that when n goes to infinity, a binomial distribution is very close to a Poisson distribution. Do you understand what I'm saying? Okay, is that clear? Is that all clear to you? Everyone? That makes sense, right? Now, can you use that ideas to solve the problem? The problem here. Suppose that 1 in 5,000 light bulbs are defective. What is the probability that there are at least 3 defective light bulbs in a group of size 10,000? What do you think? Okay, here's the problem. Okay, in order to solve the problem, what should we do? Do you know how to do that? Do you know how to solve the problem here? Suppose that X is the number of light bulbs. Okay, I'm sorry, of defective light bulbs in the group of 10,000 bulbs. Okay. Then X follows a binomial distribution with the two parameters 10,000, and then the probability is 1 over 5,000. Okay. Then we can find the probability that X is at least 3. X is at least 3, so you get 1 minus the probability that X is less than or equal to 2. Then you get 1 minus of 10,000 to 0, and then 1 over 5,000 to 0, and then 1 minus 1 over 5,000 to 10,000. Okay, and then you can keep doing that with 2 more terms. Well, but you see that you can approximate this one by a Poisson distribution, because in this case n is quite big, is 10,000, right? And then it can be approximated by a Poisson distribution with the parameter lambda. What is lambda in this case? It is the product of the two values. So you get 10,000 over 5,000, and you get 2. Okay? It is a Poisson distribution, and you want to find the probability that X is greater than or equal to 3. That is 1 minus the probability that X is less than or equal to 2. And then you come up with 1 minus the exponential. This is going to be minus 2, okay? And 2 over 0 over 0 factorial plus 2 to the first over 1 factorial plus 2 squared over 2 factorial, okay? Do you understand what I'm saying? Is there any questions so far, everybody? Okay. What we get here is 0.3233 for the answer. All right. What if I use the binomial distribution instead of Poisson distribution? Do I get the similar thing? Well, then this is what I get by using a binomial distribution. This is what I get, right? And it is very similar to the one that I just did, right? I just got here, 0.3233236. All right. Do you understand? Sent to you, everybody? Okay. Let's try the next example. Suppose that the number of drivers who travel between a particular origin and destination during in a designated time period has a Poisson distribution with parameter 20. What is the probability that the number of drivers will be at most 10? Can you get that? All right. Now, suppose that x be the number of driver who travel between a particular between the origin and destination during a designated time period, right? Then you can conclude that x follows a Poisson distribution with the parameter 20. Okay, so this is x. It is the number of drivers who travel between the origin and destination during a designated time period. Okay. Then you get you have the distribution of x, and in question A you want to find the probability that the number of drivers will be at most 10. So you get this you get the exponential minus 20, and then 20 to 0 over 0 factorial plus 20 to the 10 over 10 factorial. Okay, and then you can get the answer. All right, any questions so far? And that would be about 10%. All right, is that all clear? It is about 10%. In question B, you want to find the number of drivers will be within 2 standard deviations of the mean value. Question B. So you want to find the probability that x is between, let's say, x minus the mean value. What is the mean value? The mean of x is lambda, which is 20, and the variance of x is also lambda, right, which is 20. So you want to find the probability that x is within 2 times the standard deviations of the mean value. So x minus the mean should be less than 2 times the standard deviation square root of 20. Understand? You want to find this probability. And how about, what is this value? What is that value? You get You get 8.9 for that, I think. You get 8.9 for that. You get, this is 8.9, about 8.9. So you want to find, so this is the probability that x is less than 28.9 and greater than, what is that? I think it is 20 minus 8. So 11.9, correct? Is that clear? Let me see. Okay, let me check. 2 times square 20. Yeah. So you should get 11.1, I believe. Right? Then it is the probability that x is between 28 and then 12. Okay, that makes sense? Is there any questions? And then you can get the answer as follows. It gets about 92%. Okay, so you get 92% for this. Is there any questions? Everyone? Again? Sure, you want to find the probability that the number of drivers, which is x, will be within 2 standard deviations of the mean value, which means that x minus the mean should be less than 2 times the standard deviation. Okay, so I want to find the probability that the observed value of x minus the mean 20 less than 2 times the standard deviation. The standard deviation in this case is square root of 20. So you get 8.9 for this, and you get 11.1, actually between 11.1 and 28.9, and then you come up with this number, right? Because x is an integer, right? Therefore, x is between 12 and 28. Do you understand what I'm saying? Is it okay? Is it clear? And then you can come up with the formula, let's say e to the power minus 20, and then 20 to the 12 over 12 factorial plus unto 20 to the 28 over 28%, sorry, factorial. Then you can get this one, okay? Now, I want to give you another example regarding a Poisson distribution. Suppose that we have 10 observations here. What is the probability that x is less than or equal to 2? If I have no information, about the distribution, then what is the probability that x is less than or equal to 2? In this case, I just use the empirical distribution, right? What is the empirical distribution? In order to get the empirical distribution, I need to consider, I can say, okay, let's say you get 0, 1, 2, 3, 4, 5, and count the probability of the relative frequency. So you get 1 over 10, right? For 1, what do you get? You get 2, so 2 plus 1, so 1 over 10 plus 2 over 10, right? And for 2, you get 1 plus 1 over 10 plus 2 over 10 plus 1 more, so you get 1 over 10, right? For 2. So this will give you the particle distribution. And then obviously, the probability that x is less than or equal to 2 is simply 4/10, and you get 40%. Okay, if you have no information about the distribution, you just use the particle distribution. That's it. However, if you know that the observations follow a Poisson distribution with an unknown parameter lambda, can you get that with some better approximation? Can you approximate this probability? Can you think about that for a minute? What do you think? Well, it is, first of all, you need to estimate the parameter lambda. And we knew that lambda is the mean of x, right? And that can be approximated by the average value. So you get 3 plus 3 plus 0, all divided by 10. Okay? I think it is, let's say, 12, 22, 26. So 2.6. Then you can find the probability that x is less than or equal to 2. That is the probability that x equals 0 and then 1 and then 2. And then you get the exponential 2.6 to 0 over 0 factorial plus 2.6 to the first over 1 factorial plus 2.6 squared over 2 factorial. And then you get, what is that? Then you can say that you want to find the probability that x is less than or equal to 2. That is about 51%, okay, 51.8%. It is greater than the value you obtain up here. If you have no information about the distribution, then that probability is 40%. If you know that the distribution is a Poisson distribution, it is 51%. So I can say I can say that the probability that x is less than or equal to 2, given no information, equals 40%. Okay, and the probability that x is less than or equal to 2, if the distribution is a Poisson distribution, then that is 0.518426. Okay, my sense. May I move on, everybody? Okay, now let's move. Now we will move to the next part of this chapter regarding a uniform distribution. Uniform distributions. Well, it is not surprise to see that uniform distribution is not really useful in reality, in practice, in general, but it is really useful when you want to generate a random sample. Okay, or you can use it to get to generate some other distributions. All right, that's why we may want to we may want to talk about that a little bit. Okay. A uniform distribution. Let's consider a uniform distribution on the interval AB. It means that we have the same chance to get any value between A and B. Suppose that we have the density function f of x equals c for any x between A and B. Okay, because we have the same chance, so it should be a constant c, and this is 0 otherwise. Okay, and then you want to find we want to find the value of c. This is c, right? And then you may want to find the value of c. How can we do that? Well, the area of this region of this rectangle is 1. We knew that, right? Because the integral from a to b of the function f of x dx equals 1. This area is 1. The length of one side is b minus a. Therefore, the length of the other one should be the reciprocal of b minus a to guarantee that the area is 1. So c is 1 over b minus a. That's why you come up with this function, okay? And then you can compute the area. You can compute the area of this one, right? To get the cumulative distribution function, which is x minus a times b minus a, right? That can be obtained by computing the length of one side of the smaller rectangle, which is x minus a. This is x, right? Time the value of c. So you get c times x minus a, and c is the reciprocal of b minus a, and you get x minus a over b minus a. Okay, it is very simple and easy to see. Now I want to show you some particular some specific uniform distributions. You can have a look at it, get them over here. In this graph, there are 4 uniform distributions. The red one is showing the uniform distribution on the interval 0 to 2.5. The orange one gives you the uniform distribution on the interval 0.5. The green one gives you a uniform distribution on the interval 0.10, and blue gives you a uniform distribution on the interval -2, 2. Okay. Now you can recognize that all the distributions here are symmetric, and because they are symmetric, the mean value should be at the middle right here. Okay. Then can we find it? What is the mean value in this case? The mean value in this case, which is 5 for the green distribution, that would be a plus b over 2, right? If this is a and this is b, the mean value should be a plus b over 2, the middle point. You can also find, if you know the mean value, you can also find the mean the second moment, which is the integral from a to b, x squared times the density function, which is 1 over b minus a dx. And then you can find the variance of x, which is the mean of x squared minus the square of the mean of x. Okay, do you understand? And then by using the calculation, you can get b minus a all squared divided by 12. All right. Okay. Do you understand what I'm saying? Okay. Let's consider the following example. Suppose that X is the measurement of current, which is a variable following a continuous uniform distribution on the interval 4.9 and 5.1. What is the probability that the current is between 4.95 and 5.0? Why is that? In order to find this probability, you need to find the density function f of u equals 1 over 5.1 minus 4.9, which is 5, I think, right? Then you can find the probability that the current is between 4.95 and 5, and that is the integral from 4.95 to 5 other density function, which is 5 du. And then you get it is 0.35, right? So you get 25% for the probability. Okay. If you want to find the mean, then you can get it very quickly. The mean is simply 4.9 plus 5.1 over 2, which is 5, right? You can also find the variance of x, which is 5.1 minus 4.9 all square divided by 12, right? And you get 0.02, 0.2, right? Square, so you get 0.04 over 12, okay? Is that clear? It should be okay, right? Okay. Let's consider this example. Suppose that we have the following observations. Can you estimate the probability that x is less than 2 again? Well, if you find the probability that x is less than or equal to 2, given no information, all right, if you don't have this the assumption of uniform distribution, then you can use the empirical distribution to get that. What is the empirical distribution at the value 2? You count the number of observations less than or equal to 2, you get 1.2, 1.4, 1.6, that's all. So you get 3 over 10, and that is 30%. Okay? How about the assumptions here? What if you know that the distribution is a uniform distribution? The point is that you don't know the two parameters A and B. Can you estimate them? Can you estimate A and B in this case? Do you know how to do that? Well, in this case, you see that you can find the mean of x, which is a plus b over 2, and I can approximate it by the average value. The average value is simply 3.6 plus 1.2 all divided by 2, all divided by 10, right? And you can get a number. Understand? Okay. So the mean value of x is 3.07. Okay, and you can also find the variance of x, which is b minus a squared divided by 12, and you can approximate it by s squared, the sample variance. The sample variance is 3.6 minus 3.07. You need to compute the deviations square, and then you divide the sum by the degree of freedom, 10 minus 1. You should get the sample variance. S squared is the sample variance, and you use that to approximate the population variance. And after that, you have two equations for A and B. Then you can solve for them. You can solve for A and for B. Okay? Do you understand? And you can see that B and A are these two numbers. Okay? So you can find A and B. After finding A and B, you can find the probability that x is less than or equal to 2. Okay? And that is simply the f of 2, and then you get 2 minus A over B minus A. You already knew the value of A and the value of, and the value of B. Then you can estimate this probability very quickly. Understand? Is that all clear to you? And the answer should, in this case, is about 45%. Okay, the answer is 45%, not 30%. So if you have no information, it is 30%. But if you do know the information that the distribution is uniform, is a uniform distribution, then you get this distribution, you get this probability. Okay, 45.8%. Is there any questions so far, everybody? Is that clear, everyone? Okay. All right. Now I want to move to the next distributions that we are going to learn in this chapter, the exponential distribution. A Poisson process is a process in which events occur continuously and independently at a constant average rate lambda. So you have a Poisson distribution, right? You already knew that. The exponential distribution describes the distance or the time between events in a Poisson process. So if a Poisson distribution, if a Poisson random variable gives you the number of events that you can observe during a period of time, then the exponential random variable is simply the time, the waiting time, the time between the two Poisson events. Okay, just like you have a period of time and you count the number of events. That is a Poisson distribution. Okay. Now, if you have two Poisson events, you want to measure the time between the two events. That is an exponential random variable. Okay. There are many applications of exponential distribution in reality. The exponential distributions can be used by seismologists and earth scientists to predict the approximate time when an earthquake is likely to occur in a particular location. Or you can use the exponential distributions to calculate the reliability of electronic gadgets, such as a laptop, battery, processor, mobile phone, etc. And then it can help you to know an approximate time after which the product will get ruptured. Okay, or you can use the exponential distributions to calculate the time duration between the passing of two consecutive cross, thereby helping the traffic in charge to reduce the traffic problem and to avoid collisions. Okay, so just like you can find the time between the two cars, right? Like you have you get the detector right here. You have a car coming, right? And then you wait until the next car crossing this point. The time between those two events may follow an exponential distribution and so on. Okay. Now we can well, there is a relation between a Poisson distribution and an exponential distribution. Suppose that x is the length from any starting point on the y until a flaw is detected. Do you remember the problem? The problem of counting the number of flaws that you can observe in one or 5 millimeter wire. Do you remember that? That we learned in the previous part of the chapter about Poisson distributions. Then suppose that actually the length from 2 points. Okay, let's say 2 points here. You count. So that is the length between the two flaws is x, and n is the number of flaws in u millimeter of wire. So if the mean number of flaws is lambda per millimeter, then we can find the probability that x is more than u. What is that? The probability that x is more than u is the probability that x is more than u is the probability that you can you find no flaws in this part of the wire. Do you understand? Is that clear? Suppose that this is u millimeter. Okay, suppose that it is u millimeter wire. X is more than u. This is 0. X is more than u. X is more than u. It means that x is over here. Okay. If x is here, it means that the length between the two flaws is greater than u. It means that the number of flaws within an interval of u millimeters of wire contains no flaws, right? And then it means that the capital N is 0. The number of flaws is 0. So you have the equation. The probability that x is more than u is the probability that the capital N is 0. What is n, by the way? Capital N is a Poisson random variable, right? Because it is the number of flaws that you can observe in u millimeters of wire. And in 1 millimeter of wire, you can observe lambda flaws. So in u millimeter of wire, you can observe lambda times u flaws. It means that n follows a Poisson distribution with the parameter lambda u, right? And then you get the following probability. That is the exponential minus lambda u times lambda u to 0 over 0 factorial. And that is the exponential minus lambda u. And then you can find the probability that x is less than or equal to u, which is 1 minus the probability of the complement. So you get 1 minus a to the power minus lambda u. Okay? And this is the cumulative distribution function of the capital X. Then you can differentiate both sides of this equation, or just differentiate the function f of u to get lambda times minus lambda u. And that is the density function of the random variable x. Do you understand that? Okay. So we can say that an exponential distribution has the following probability mass function, probability density function, and the cumulative distribution function. This is what you get for that. Do you understand? Okay, this is the density function, and this is the cumulative distribution function. Okay, we can draw some graph of the exponential distribution so that you can get some idea about the distribution. If lambda is 1, then you get if lambda is 3.5 greater, then the you get the blue curve, right? And if lambda is 9, you get the sign 1. Okay, so it is closer and closer to the y, the vertical line. Okay. Any questions so far? Any questions? Now I want to give you some properties. This is not all interesting properties of the exponential distribution, but I don't think that we can go over all of them. So I just introduce you just two the more important properties of the exponential distributions. First, if x follows an exponential distribution with the parameter lambda, then you can prove that the mean value is 1 over lambda. That is very easy to prove. Why? Well, the mean of x is simply the integral from -infinity to infinity u f of u. And then you get the integral from 0 to infinity only, right? Because if u is less than 0, the density function is 0. If u is more than 0, then can you tell me the density function? What is that? The density function in this case is lambda times the exponential minus lambda. So you get lambda times the exponential minus lambda u. Okay, and you can do the calculation to see that it is 1 over lambda. All right, you can also find the mean of x squared, which is the integral from 0 to infinity u squared lambda times the exponential minus lambda u du. Okay, any questions so far, everybody? And then you should get 1 over lambda squared. Let me see. You get this way. You get 2 times 2 over lambda squared. Okay, and then you can conclude that the variance of x is the mean of x squared minus the square of the mean of x, right? And then you get 2 over lambda squared minus 1 over lambda squared, and you get 1 over lambda squared for the mean for the variance of x. So the variance of x is 1 over lambda squared, and then the standard deviation of x is the square root of the variance. It should be 1 over lambda. Okay, so you see that for a Poisson distribution, the mean and the variance are the same, right? In an exponential distribution, the mean and the standard deviation are the same. Do you understand? Okay. Is that all clear? Now I want to introduce to you the memorized property. It means it says that the probability that x is more than s plus t, given that x is more than s, is equals to the probability that x is more than t. What does that mean? What does that mean? It means that if you already wait as unit, okay, as seconds, for example. If you have waited for s seconds, then the probability that you have to wait you have to wait for at least s plus t seconds. Is the probability that is the same as the probability that you have to wait for t seconds, counting from here. Do you understand? Do you understand what I'm saying? Is that clear? Okay. If you are ready, if you have waited for s seconds, then the probability that you have to wait for at least s plus t seconds, counting from this point, this time, is the same as the probability that you have to wait for at least t seconds, counting from this time. Okay. All right. That is the way we that is the formula we get. Now let's consider the following example. In a large corporate computer network, user logons to the system can be modeled as a Poisson process with a mean of 25 logons per hour. What is the probability that there are no logons in the next 6 minutes? Question A. Suppose that x is the number. Suppose that x is the time. The time in, let's say, in hour. X is the time in hour. Okay, x is the time in hour between two logons. And follow. If you consider, let's say n is the number of logons in an hour, then n follows a Poisson distribution. The parameter lambda, what is lambda? Lambda is the average number of logons in 1 hour, and you get 25. Okay. Now, in question A, if you want to find the probability that there are no logons in the next 6 minutes, what do you think? In that case, I need to change the variable here. I can say y is the number of logons in only 6 minutes, correct? And then I can see that y follows a Poisson distribution with the parameter lambda. What is lambda in this case? In 1 hour, you observe 25 logons. So in 6 minutes, you can observe 2.5 on average. 2.5. Find the probability that y is 0. That you find no logons in 6 minutes in the period. The exponential minus 2.5 times 2.5 to 0 over 0 factorial. Besides, you can get that by using then you can see that in this case lambda actually follows an exponential distribution with the parameter lambda, and lambda is the number of logons in 1 hour, right? Because the unit here is in hour. So you get 25 for this, and you want to find the probability that the time between two log-ons is at least the time is at least 6 minutes, is more than 6 minutes, right? Okay, or let's say 0.1 hour. Okay, the probability that there are log-ons in a period of 6 minutes is the probability that the time between two log-ons is more than 0.1 hour, 6 minutes. Okay, that you can do different function right here to get I get a to the minus lambda, which is 25 times u, 0.1, and I should get exactly the same thing. Do you understand? So I get, in this case, e minus 2.5. Get the same thing. Is that clear to you? Is that clear, everybody? Is that clear? For question B, I think it's very similar to the activity B, right? So I want to find it should be f of 3 minus f of 2, something like that, and you get 1 minus e minus
Teacher. Teacher.
Yes.
Your connection is not stable. We cannot follow what you're saying about. Like the screen is freeze.
You don't. Can you hear me clearly? Everybody?
Yes.
Can you hear me? Okay.
So
do you understand what I said over here?
Again, from question A, like we lost the connection from that question.
Okay. So you mean this problem? You want me to go over this problem?
Yes, yes.
Okay. Well, first of all, you have this model, Poisson model, right? The probability that there are no log-ons in the next 6 minutes. So there are two ways to deal with that. First, you can use a Poisson distribution to do that. Suppose that capital N is the number of log-ons in an hour. Then capital N follows a Poisson distribution with the parameter lambda 25. Make sense? Do you understand that?
Yes, yes.
Yes? Okay. Now, if but I don't the number of log-ons in 1 hour. I want to find the number of log-ons in only 6 minutes, right? I want to count the number of log-ons in 6 minutes, in a period of 6 minutes. So I denote by y the number of log-ons in 6 minutes, right? And that number should follow a Poisson distribution, with the parameter 2.5. Why 2.5? In an hour, there are on average 25 log-ons. Then in 6 minutes, there should be 2.5 log-ons on average. Do you understand what I'm saying? Do you understand?
Yes, yes.
Okay. Then you want to find the probability that there are no log-ons during that period. So you want to find the probability that the number of log-ons in 6 minutes is 0, right? So you want to find the probability that y equals 0. And that is the exponential a minus 2 to the power a to the power minus 2.5 to 0 over 0 factorial. In this case, I don't use the exponential distribution. I only use to get that answer. Is that okay?
Yes.
Is that clear? Okay. Now, what if I use the exponential distribution? So instead of counting the number of log-ons in 6 minutes, I measure the time between two log-ons. Do you understand that? Instead of counting the number of log-ons during a period of 6 minutes, I measure the time between two log-ons. That is x, okay? Suppose that the time is x. Then x follows an exponential distribution with the parameter lambda, which is 25, okay? And then you can find the probability. You want to find the probability that there are no log-ons in 6 minutes. It means that the waiting time is more than 6 minutes, right? So that is the probability that x is greater than 0.1. And then you can get the exponential of minus 25 times 0.1, and you get exactly the same thing. Do you understand? You get that?
Yes.
Is it all clear? Is it clear? You guys, is that all clear? Oh, I'm going to send you guys the updated version concerning the exponential distributions. Is it okay now? Is it good? All right. Oh, the sample variance, you can go back. For the sample variance, you can go back to the previous chapter. When I introduced you the concept of variance, I think I already gave you the formula for the sample variance, the S squared. So it is simply over n-1. That is the sample variance. Okay. In question is the second problem. You want to find the probability that the time in between 2 and 3 minutes. So you want to find this, but you need to replace because x is in hour, so I need to replace 2 and 3 by hour, not minutes here, right? This is minutes, but you want to find you want to deal with that in hour. So I'm going to say it is what is that number? 2 minutes means 2 over 60, right? Okay, and 3 over 60. So you get 3 over 60 here, and then 2 over 60. All right, and then you can get 1 minus the exponential. The lambda is 25, so minus 25 times 3 over 60, right? And then minus this for the f, then 1 minus the to the minus 25, 2 over 60. All right, and then you should get the answer for that. It is easy, so we'll leave it to you. I will skip question C. I want to talk about question D. What are the mean and the standard deviation of the time logging? In question D, you want to find the mean value of x, and that is 1 over lambda, so 1 over 25. All right, and the variance of x. I'm sorry, we want to find the standard deviation instead of the variance, right? The standard deviation. So it should be 1 over lambda as well. So it should be 1 over lambda, and you get 25 on either. All right, same thing. Any questions so far? Everybody? That is okay, right? Okay, let's have a break. Then after that, we can continue with the next example. Well, in question B, in question B, you get probability that x is greater than 2/60, less than 3/60. Probability that x is less than 3/60 minus the probability that x is less than 2/60. We don't really care about the equal sign here because it is a continuous distribution. And then you should get the f of 3/60 minus f of 2/60. Okay? Is that okay? Okay. All right, let's have a break. Then we will continue with the next example, this one. Can you solve the problem? Can you solve the problems? You get 0.3003. Okay, let's see. X is the exponential is an exponential random variable, right? Where X is the time between detections of particle with a Geiger counter. So you get you see the mean of X is 1 over lambda, which is 1 over 1.4. Sorry, it's 1.4. So lambda is 1 over 4 over 1.4, right? After you find the value of lambda, you can find the probability that a particle is detected in the next 30 seconds. So the time between this detection of a particle should be less than 30 seconds, and we are working on and the unit we are using is minute. Then this should be 0.5. Okay, 0.5 minutes. This is what you want to compute, and that should be 1 minus the exponential minus lambda u. So you get 0.5 over 1.4. Okay. That all clear, everybody? All clear, everybody? Is it clear? Is it all clear? Okay. So this is what we get for the answer, 0.3003. All right. All right. Good. Let's consider the next example. In this case, you need to use the memoryless properties of the exponential distribution. Suppose that a number of miles that a car can run before its battery wears out is the lifetime of the battery. The lifetime in miles of the battery. Then an X follows exponential distribution, correct? X follows an exponential distribution with the parameter lambda. Here, the mean of X is 1 over lambda. Okay, and that is 10,000. Can you hear me now? Hello, can you hear me? Hello? All right, that's better, right? I don't know for some reason. So suppose that X is the lifetime in miles of the battery. Then X follows an exponential distribution with the parameter lambda, where X is 1 over 1,000, right? Okay. And suppose also that S is the time, that S is the number of miles, that the car, or let's say the battery, has been used. Okay. Then you want to find the probability that the lifetime of the battery is greater than S plus 5,000, right? S plus 5,000, given that X is more than S. Do you understand that? Okay, X is more than S, because it has been used for S miles, and it is still okay for now. Then the lifetime must be greater than S, and you want to find the probability that X is greater than S plus 5,000, given that X is more than S, right? Because you want to use an addition on, you want to use more than 5,000 miles. So you get this is the probability that X is greater than 5,000, right? Is that okay? Good. Can you see the screen right now? Can you see the screen? Hello, can you see the screen? Can you see it now?
Yes.
Okay. All right. And because X follows an exponential distribution, this becomes that makes sense? Okay. Any questions so far? And then the answer should be minus, it should be 0.60653. Okay. All right. Okay, now I want to move to the last distribution that we are going to learn in this chapter, normal distribution. And in fact, I saved the best for last. This is the more important distribution that we can learn in probability and statistics. Let's go back to two graphs of binomial distribution and Poisson distribution. When n is 50 and lambda is 20, you see that these two distributions are different. Of course, they are different. The two distributions are different. Okay, the range are different. The heights are different. Right? The kinds of distributions are different, but they look very similar to each other, right? They have a bell shape. Both of them have bell shape. So you think they might be close to a family of distributions, right? And in fact, it can be proved that they are very close to when n is big or lambda is big, they are very close to a family of so-called distribution with two parameters, m and sigma square. All right. Okay. A random variable x is called to be of our distribution with two parameters m and sigma square if its probability density function satisfies this equation. F of x equals 1 over sigma times the square root of 2 pi the exponential minus x minus m squared over 2 sigma squared, where m is the mean of x and sigma squared is the variance of x. Okay. The way they got this function is to find the limit of the limit of a sequence of binomial distribution or Poisson distributions. Okay, then you should be able to get that formula. Then we can standardize a normal distribution x by considering x minus m over sigma, and we can prove that y follows the standard normal distribution. In this case, the random variable y is called a random variable of the standard normal distribution, or simply the standard score of x. Okay, we can verify that very easily. Suppose that x follows a normal distribution m sigma square. All right, then you come up with this distribution. Then I can let's say I consider x minus m. Then I move it to the left m unit. Then you can see that it is still a normal distribution, right? It still has a bell shape like that. And then you divide, if you divide x minus m by sigma, then you scale it. You still have something similar, and it also has a normal distribution. All right. So we can say that y follows a normal distribution with a mean a and the variance v. Can we find the value of e? E is the mean of y, which is the mean of x minus m over sigma. Okay, and that is 1 over sigma times the mean of x minus m, right? Do you understand? All right. Okay, and then you come up with 0 because the mean of x is 0. All right. Okay. How about the variance of x? The variance of xv is the variance. I'm sorry. The variance y is the variance of x minus m over sigma, and that is 1 over sigma times the variance of x minus m, and this becomes 1 over sigma squared, the variance of x. And because the variance of x is sigma squared, this becomes 1. So I can conclude that y follows the standard normal distribution with the mean 0 and the variance 1. And I call it this special distribution the standard normal distribution. Okay. All right. Okay. Then you can see that you get the if you standardize a random variable, a normal random variable, you can get the standard normal random variable like this one. Okay. And the density function of the standard normal distribution is simply 1 over square root of 2 pi times the exponential minus x squared over 2. Okay. Here are some graphs of normal distributions. All right. If the mean is 0, the variance is 1. Then you get the black curve. If the mean is 0, the variance is 9. Then you get the feather distributions, right? The variation of the normal distributions is bigger, right? Because the variance is greater. And for the blue one, you get the mean minus 10. The variance is 9. It's the same as the variance of the red one. So you see that they have the same shape, right? But at the different locations. Now I want to introduce to you the definition of the cumulative distribution function for a standard normal distribution. Capital phi of x is the integral from minus infinity to x of the function f u du, where f is the density function of the standard normal distribution. All right, and I put them here for your information, so I'm going to skip that. But I want to introduce to you the concept of Z alpha. Z alpha is called the upper alpha critical point, and that is the point such that the area to the right, the red region, is alpha. Okay, so if you have the curve like this one, and you get that one is 0.01, this point is denoted by Z 0.01. Okay, and you call it the upper 0.01 critical point. Do you understand? Do you understand what I'm saying? Is that all clear? Okay. Is that all clear? Okay. Again. Well, again, the cumulative distribution function of the standard normal distribution is denoted by capital phi of x. All right, and for Z alpha is called the upper alpha critical point of the standard normal distribution. It is the point such that the area to the right is alpha. So this is alpha. Okay. So if the area over here is 0.01, then you call this point, you denote this point by Z 0.01. That's all. It's just the notation. All right. Let's consider the following step. Suppose that the current measurement in a strip of wire follow a normal distribution with the mean 10 and the standard deviation 2. What is the probability that the current measurement is between 9 and 11? And then determine the value for which the probability that a current measurement is below this value is 98%. Can you get the answer, you guys? Can you get that? Zero point 383. Let's see. Here we assume that X is the current, okay? Then X follows another distribution with the mean 10 and the variance 2 square. Then we can say that X minus 10 over 2 follow the same number distribution, right? And then you want to find, I would say that is Z, and I want to find the probability that X is between 9 and 11. So between 9 and 11, and that is the probability that I'm going to standardize that to get X minus 10 over 2 more than 9 minus 10 over 2, less than 11 minus 10 over 2. And then you come up with the probability of Z more than minus 0.5, less than 0.5. Okay? Do you understand? And then you get the integral from minus 0.5 to 0.5. The density function you need to use is 1 over square root of 2 pi a minus u squared over 2 d, right? And then you can use the calculator to get the answer. So I will skip that part. Question B. Question B. You want to find the point the point u such that the probability that X, you want to find the value u for which the probability that a current measurement is below this value is 0.98. So you want to find u such that this probability is 0.98. I want to find u such that the probability, this probability is 0.98. And then I get the probability that X minus 10 over 2 less than u minus 10 over 2 equals 0. And this is the probability that Z is less than a number. It should be 0.98. Okay. And then you can use the table for that. It is the table, the statistical table. And then I'm going to use this one. You can look for it. You can look for the table on the Learning. You can see that this, okay, let's consider this value. Wait, this one. 0.614092 is simply the probability that Z is less than, what is that? 0.29. 0.29. Okay. Or I can say this value, 0.684386 is the probability that Z is less than or equals to 0.48. 0.48. Understand? Now I want to find the value such that the probability that is less than that number is 98%. So I look for 98%. What is 98%? 98% is, where is that? Right here. I have two numbers. And which one is closer? Which one is closer to 98%? I think the second one is close. The first one is closer, right? So I come up with the 2.05. So I can conclude that U minus 10 over 2 is 2.05. And then I conclude that U is 14.1. That is the final answer. Do you understand? Do you get that? Do you get it? Okay. All right. Now I want to discuss a little bit further about number distributions. Suppose that X follows a number distribution, and then you can conclude that you can say that Y follows a number distribution with the mean A and the variance B. Okay, you can see that A is the mean of Y, which is the mean of AX plus B. So you get A times the mean of X plus B, and that is A times N plus B. Okay. Besides, the variance Y is the variance of AX plus B. So you get A squared times the variance of X. You can remove B without any problem, and that is A squared times sigma squared, right? Because A is sigma squared, right? Right here you can see that the variance of X is sigma squared, and the mean is N. So you can say that the variance. So I can conclude, I can get the distribution of Y. Okay, it's with the mean. Okay. On the other hand, if you have the xi, they follow number distribution with the mean mi sigma square I, and they are independent. Then the sum of xi will follow a number distribution as well. The mean is the sum of the means, and the variance is the sum of the variance values. So in general, I have the following results. This is the summary of what I just mentioned. So you knew that the mean of X is N, the variance is sigma squared. If X follows a number distribution, you can get the distribution of AX plus B. If xi follows a number distribution and they are all independent in this assumption, then the sum will follow a number distribution, and the mean is the sum of the means, the variance is the sum of the variance values. Okay? Is there any questions? Let's consider this example. Suppose that X follows another distribution with the mean M, with the mean 5, the variance 9. What is the distribution of Y 2X minus 6? Can you get that? Well, in this case, you can see that the mean of x is 5, the variance of x is 9. Then I can conclude that the mean of y is the mean of 2 times the mean of x minus 6. And it gets 2 times 5 minus 6, and you get 4. Okay. In order to get the variance of y, I get the variance of 2x minus 6, and it gets 4 times the variance of x. The variance of x is 9, so this is 36. Therefore, I can conclude that y follow the standard the normal distribution with the mean 4 and the variance 36. Okay? Is there any questions? Anyone? Okay. Is that all clear? Is that clear? All right, so let's consider the next exam. Okay, so in this case, you have x1 plus x2. Then plus so you get 1. Okay. The variance of x1 plus x2 is the variance of x1 plus the variance of x2. Okay, and that is 4 plus 5, and you get 9. All right, so the distribution of x is a number distribution with the mean minus 1. The variance is 9. So question B, I need to find the mean of x1 minus x2, and I get the mean of x1 minus the mean of x2, and that is 2 minus -3. So I get 5 for this. The variance of x1 minus x2 is simply the variance of x1 plus the variance of minus x2. It's the same thing. So you get, you still get, what's that? You still get 2, and plus you still get 4 plus 5, and it is 9. The same, okay? So the balance of the sum is the same as the balance of the difference. All right. Then x1 minus x2 should follow a normal distribution with the mean 5 and the variance 9. Okay. For question C, it is very similar. If you have the mean of 3x1 plus 4x2, then that is 4 times the mean of x1 plus 3 times, sorry, 4 times the in order to get the value 3x1 plus 4x2, you get 9 times the variance of x1 plus 16 times the variance of x2. Then you can get the answer from here. Okay, I will skip the calculation. All right. Any questions so far? Is that all clear, everybody? Okay, so if you have no further questions, let's stop here and see you next time. All right, bye. So today we just finished the your midterm exam. Well, we almost finished that. We need one more part of the central limit theorem, then you should be okay for the midterm exam. Yeah, I will upload the latest version. Not right now, but I'm going to create a quiz, and it will be available soon, and you should be able to do it perhaps today, or and the deadline will be tomorrow. Okay.